Good morning, friends. It gives me immense pleasure to be here again for my favorite course, Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I am in the last phase of my course, Engineering Thermodynamics, and I have completed the 4 module, and now I am in the 5th module, and in the 5th also I am in the 5th lecture today. In this, I will be discussing about one-dimensional steady state conduction, and I will be discussing about the resistance method of calculating the total heat transfer rate. So these topics I will be covering in this is one-dimensional steady state heat transfer, derivation of the one-dimensional equation, resistance offered by the conduction, resistance offered by the convection, total resistance in multiple phases, total resistance in composite wall. So these I am going to discuss today. And before the last class, I have discussed about energy balance. The energy balance means how much you are putting in, how much energy is going out, how much energy is generated, and how much it is stored. So if you see here, input minus output plus generation is equal to accumulation. This is the simple energy balance, and in this way we have already find out the equation for energy balance. Derivation of the energy balance for heat transfer we have done. Boundary condition also we have seen that at x is equal to 0 it is constant temperature, constant flux, variable flux. All these things we have already done with. We have also find out the Newton's cooling law. So in this cooling law, Q convection is equal to H AS Ts minus T infinity. So this also we have done, and the relation between K and H we have already find out during our previous class. In today's class we are going to discuss about one-dimensional steady state conduction and this equation. So one dimension, if you see, only we will see the x direction. Here is the slab. The surface of the slab is having the temperature T1, and here it is having the T2. At x is equal to 0, it is the 0, and at the end it is x is equal to L. L is the total length of this slab. So for one day steady state conduction, conduction takes place in the direction of the low temperature. The general energy balance is given by which we have find out in my previous class. You can refer just before this class, I have done that. So here del square T plus Q by K is equal to rho Cp by K, dou T by dou small t, where this small t is the time. So once we talk about the steady state, for steady state, there is no change in this. So del capital T by del T is equal to 0. There is no loss or gain of the heat. So Q generation will be also 0 here. So we will have del square T is equal to del square T by del x square, and Q dot is equal to 0. So we can write this as a K del square T by dx square is equal to 0. So this is the partial differential equation. To solve this, we need the boundary condition or needed. So boundary condition in this case is at T x is equal to 0 is equal to T1, and at T x is equal to L is equal to T2. So we have the T1 and the T2. Two boundary conditions are given. So if you solve this, you will get T is equal to T2 minus T1 into x by L plus T. This is the solution of this equation which we have find out here T is equal to T2 minus T1 into X by L plus T. This is the solution for 1D energy equation. So now heat transfer rate in 1D and resistance due to conduction. So how much resistance we are going to get? So we are going to find out this thing. So here we can see we are going to find out heat transfer rate, that is Qx in x direction, only as it is a 1D case. To quantify the heat transfer rate, how much is the amount of heat you are going to transfer? Let's see. We know that Qx is equal to minus Ka dt by dx, where dt by dx we can write T2 minus T1 by L, where L is equal to length of the slab. So here we can write minus Qx is equal to minus Ka T2 minus T1 by L. So this we got the Qx. Now we can find out the resistance. One has to look at resistance offered towards conduction. It is R or RC because it is a conduction, so anyone you can use it. So this R is equal to net change in temperature divided by Qx. So this change in temperature T1 minus T2 divided by Qx is equal to minus Ka T2 minus T1 by L. So we can write here L will go up, T1 minus T2 into L divided by Ka T1 minus T2. T1 minus T2, T1 minus T2 will be cancelled. So you will get resistance R is equal to L by Ka. So for the conduction, it is a resistance offered by conduction. Okay, so this R is equal to L by Ka due to the conduction. So this we have got the first relation, the first relationship R is equal to L by Ka, and R is equal to, we can find out from delta T by delta X. Delta T is a temperature difference and Qx is equal to your heat transfer rate. Now the resistance due to the conduction RC is equal to R L by Ka. For resistance, not only K but length of the slab and area A. So here length, area and K are important for the conduction. Therefore, we can make a simple resistance network like the electrical circuit. So if you take the slab which we have already taken, so this is the T1 and this is the T2. So if I make here, this is the resistance offered, this is the T1, this is the T2 and here is the Qx. So this will be, resistance will be L by Ka. Okay, this is represented here, that in this way we can represent, if there are number of slabs, we can add in the same way L1 by K1, Ka1, Ka1A, L2 by K2A, like this we can add it. So the resistance is directly proportional to the length. So as much you have the more length, that much you have the more resistance, and it is inversely proportional to the area. So area is what? This is the area. This area will take part. So if this is the X, this is the Y and this is the Z. So Y and Z, Y into Z will be the area here. So this is depend upon the inversely proportional. So as you increase this, resistance will be decreasing. But as you increase this X distance, that much resistance will be increasing. And as you reduce this, increase this, that much resistance will be decreasing. And if material is different, then also it is, so L means length in the direction of the heat flow, that is the length, and perpendicular to that is the area. So if here X, Y, Z, so Y, Z is the area, not the L. L will not be counted. L will be taken on the numerator and A will be taken as a denominator. So resistance due to the convection. So as of now we have seen that resistance due to the conduction is equal to L by Ka. Now we will see that when the resistance for the convection, when different fluids are there, fluids and solids, and heat is transferring, what will happen? So how much it is going to take the resistance. Now if fluid is hot at one end and cold at the another end, having temperature T infinity 1 and T infinity 2 respectively, this is the 2 respectively, using the Newton's law of cooling. So here there is a slab, this is the slab, X is equal to 0, temperature is T1, X is equal to L, temperature is T2. At this fluid, it is the hot fluid, T infinity 1, it is hot, and it is a hot water, and here is air. This you can see, it is air, it is cold. T infinity 2 at the cold. The H is the thermal convective heat transfer coefficient here, and here H2 is the convective heat transfer here. So by the Newton's law of cooling, Q rate is equal to HA T infinity minus T1 for this zone. For fluid hot to the slab, system cold. Now convection heat transfer, R convection is equal to, we can write that T infinity 1 minus T1 by Q. So T infinity minus T1 divided by Q is equal to HA T infinity minus T1. So this is cancel. So R conduction is equal to 1 by HA. So we got another equation for the resistance, which is a convective resistance. It means from fluid to the solid or solid to the fluid, we have to use this equation. Now to draw the resistance network of this, here we can see that from hot one to the cold one, from cold one to the another hot one, and this hot one to the cold air one. So here 1, 2 and 3. So here T infinity 1 here to the T1, that is the 1 here, here to here. Next T1 to T2, that is the, so here it is 1 by H1A. From T1 to T2 it is L by K, it is a conduction. This is the convection. This is also convection. So we can draw the resistance line that from here T infinity 1, then it will go to the fluid. Fluid is 1 by H1A up to reach to the surface here T1. From this T1 here to this T2, from here to here, it is a conduction. So this will be L by Ka. We will make the resistance. It will reach to the T2. From T2 to H2, T infinity 2. So here 1 by H2. H2 is the here. This is the H2 is the convective heat transfer. So we will get here 1 by H2A. That is the power of the resistance method. A very, very important and very effective method to find out the total resistance. If you know the total resistance, you can find out the rate of heat transfer also. So rate of transfer, this you can do by T infinity 1 minus T1 divided by R. So like this, you can find out all the required parameter by using this type of method. So now if you want to make the overall resistance, this R is equal to total change in the temperature from T infinity to T infinity 2 delta T by Qx, overall temperature difference divided by overall heat transfer. So this R is equal to 1 by H1A plus L by Ka plus 1 by H2A. Here if we know any measurable quantity, that is the purpose of any modeling. So if we know anything, H1A area we know, this we can measure the object, we can find out the material this, so we can, so it is very good modeling technique. Like geyser temperature we can measure. Can we make the mathematical equation? Now to find some complex problem of the composite wall. Suppose we have a metal insulation, fluid, etc. Then how to calculate the total resistance? So we will see now for the composite wall how to find out these all things. So this resistance of a composite wall. So let us take an example of the composite wall. Suppose we have an insulator where we have a multiple walls with different properties like K1, K2 and the K3. So here we have the 1, this is the 2 and this is the 3. This is the material with the K1 conductivity. This has got the K2 and this has got the K3. Their wall temperatures are T1, T2, T3, T4. The hot fluid is flowing at the temperature of T infinity 1 with the convective heat transfer is H1, and here it is for the cold one, that is say air, and this is the hot water. So the heat is transferring from here to here and it will move from here to here. So in this way, how to draw the and how will be the profile. So if you see here at the T1 at x is equal to 0, this is the T1, and it is x is equal to L, this is the T2. So it will go like this. It is profile of the temperature will be like this. Temperature distribution will be like this. This is shown. So now we can draw the resistance of this circuit. So here is a T infinity 1. Then this is the 1 by H1A plus here L1 by K1A. Area is constant here. Then we have the L2 by K2A plus L3 by K2A plus 1 by H2A. So this is the your total resistance we will can get. In this way we can find out the total resistance of the heat transfer, and we can find out that Qx is equal to T infinity 2 minus T infinity 1 divided by R. So this is a very good modeling. Good modeling we can do for any real system. So we will see that in next class. We will see the simultaneous heat transfer mechanism. Then numerical 1, heat transfer from human body to the atmosphere. Numerical 2, heat transfer from human body to atmosphere. And these are the references, that is P.K. Nog, Engineering Thermodynamics, McGraw-Hill's 4th edition, Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Any questions, you are welcome to ask. My email ID is ydwedi@gmail.com. Please do like and subscribe this channel. I am trying my level best to give you some knowledge. If you like it, please like it and subscribe it. Please also do comment so I can improve my way of teaching. Till then, goodbye. Thank you. We will be meeting you soon with some numericals in my next class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.